Hello, hello. I don't know if you can hear me. Let me first check if the audio is clear or something. Wait. Hello, 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 hello. Let me check it on. I don't know. Yeah. I think it's very clear, I guess. Wait a second. I'll open chat for my this thing. Yeah. I can see the chat. Hello. The math exam on 9th December. Yeah, all the best for that. He, yeah. I think let's start only, no? It's better. So, I'll be teaching on Excel and some things I will not type. Like, yeah, like the mathematical equations. Obviously, it will take a lot of time. I have my own notes, which I'll copy paste and show you the things. And if you are having doubts in English, like if I can't reach you through English, you can tell me in the chat. I'll just write any Hindi stuff. If you, I can explain it in Hindi also if you want. So let's first start even before what's a group, right? So our whole thing here is based on groups. Groups. That's what we are studying. So, okay. So even before we are starting with groups, we should first start with permutations. What is a permutation? Okay. What is a permutation? Like, yeah, permutation is basically, let's say if I have a set of 1, 2, 3. Okay. So this is my set. Let's say 1, 2, 3. Now I can rearrange this set in any other way, right? Let's say if I write this set as 2, 1, 3. So this is kind of a this one, let's say let's name this as A2 and let's name this as an A1. So A2 is like a permutation of A1. Now if you have done basic math in your 11th, 12th, you know how many permutations can we do. So basically, if let's say there are n elements, that means I can make how many permutations? N factorial permutations. I don't think I need to show any proof for this one because it's very rudimentary, right? So, and permutations basically, like you can explain permutations. Let's say this is one set and this is one set. Okay. So permutations is basically in short, you can say it's nothing but a bijective function. Why do I call it a bijective function? Because historically speaking, the word permutation came before bijective function. So people before we know right what is a bijective function now. But even like bijective function means what? Onto function, as in like domain will be covered, and one to one means every one in the what do you call it? Every element in this domain will have an element in the codomain. So that's bijective, right? So for bijective, let's say in permutation, it actually means, see, we are in permutations, we cannot omit anything, na? We can't omit anything. Let's say, I'll draw this one. Okay, let's say this is, wait, can I change the stroke width? Yeah, I can. So let's say 1, 2, 3, right? This is, let's say, our domain. Now we are mapping 1 to 1. So like 1 will be mapped to 2, 2 will be mapped to 1, and 3 will be mapped to 1. So let's say I am writing 1, 2, 3 here. So 1 gets, I think 1 gets mapped to 2, 2 gets mapped to 1, 2 gets mapped to 1, and 3 gets mapped to 3. So this is what permutation is. Permutation at the end of the day is a bijective function. Okay. So you have to realize this, that we are working with bijective functions. So this is what permutation is. Now you might ask, are we studying groups, but why are we studying permutations? Because you'll get to know why we are studying permutations first at the end, because it's like a story. Okay, so I can't skip to the end and give you a spoiler. So permutation is nothing but a, what do you call it? Permutation is nothing but a bijective function. I think you have understood this. So in as a bijective function, we can think of it like this. Now, in permutations, what we do is that we select a like a generic starting position. So let's say if we took a starting position of 1, 2, 3 here, right? So that's our A1. Okay. How we write permutations like this? How can I write this? Yeah. So let's say first you have to write the 1, 2, 3, and whatever the permutation is. Let's say um, give me anything 3, 1, 2, right? So this is my any random permutation. Let's say A4. So permutations are written like this. The first main thing, just say you're making the stuff, and next one is this. This is what permutation basically is. If you have understood. What app is this? This is a Excali app. So seeing if I'm missing anything. Give me 1 second. So mm because I have my own notes which I am actually like I have my own notes open from which I am telling you guys. Now permutation has some like what do you call it? Features which I will tell you. The first feature will be that let's say if I have a group of all permutations, I'm writing a set. Okay, I'll not define group right now. Let's say I have a set of perms which will have what? A1, A2, and so on. It will have all the permutations. This set of permutation, let me name it as G. Okay, so this is my set of permutations at first. Hi, hi. And now what I want to do is that try to define some characteristics of this set of permutations that is G. Now, logically, if you think that, if you remember that, let's say I'm writing A1 as 1, 2, 3, right? Now, whatever permutation it is becoming, let's say if it is given 3, 1, 2. So basically, if I apply permutation to any element in this, we will always get an permutation in G. That means what? My first criteria, if you didn't understand this basically means कि whenever you have like if you let's say add permutation of like in this one see 1 2 3 got mapped to 2 3 1. Now let's say if there was some other A3 which was 3 1 2. Okay, so I can get 3 2 3 1 2 from A2 also, no, like from the if I do this. So let's me draw this. I'll just copy paste this, wait, 3 2 wait, let me copy paste it, and 1. So now in our A3 will be what? 2 is getting mapped to 3, then 1 gets mapped to 1 and 3 gets mapped to 2. So if you see, if I apply a permutation after a permutation, so let's say if this is a permutation A, and if let's say this is a permutation B, so if I apply this function where let's say if A permutation B, I'm writing dot. So I'll write P. We get some C. Let's say this one is a C. So this C is also belongs to G. So that means what? I'll write up certain things here. Permutations are first criteria follow closure property. So if you see, it will follow closure property. That's the first thing. Second thing, does an inverse exist? Now this is very obvious. How? Inverse exists. This is very obvious because permutations are nothing but bijective functions, right? So if we could go from, let's say, if we could go from here to here, then we can also go from here to here. Bijective functions will always have an inverse. So here inverse also exists. And finally we can say that there is an identity element. What is the identity element? So what is the identity element here? The function itself. How can you get the same function? Let's say I have 1 2 3, right? 1 2 3. Then permute that with 1 2 3. You will get 1 2 3. Identity element. What does identity element mean? Identity element actually means that, let's say I have some x, and when I do the operation and with that identity, we will get x. That is the thing. So like here, the identity element will become what? Identity of x is nothing but x itself. So the permutation itself. So remember this, that permutations follow closure property, inverse exists, and identity exists. So this okay. So this is called a permutation set. Okay, basically, and now if we formally define this, what I have been teaching you for this long time, this set of permutations G is nothing but called a permutation group or symmetric group. This thing. Okay, whatever I have been teaching you is called as permutation group or a symmetric group. So let's say if you're making normal permutations and it follows these three, I'm not writing the math equations, but if it follows closure property, inverse exists, and identity element exists, we can say that is a permutation group or a symmetric group. So I think you have understood what permutation group and identity permutation and symmetric group are. But I'll check chat now. Like if anybody has written anything. मेरा कल डीएसए लैब है मैं सिर्फ ऑल द बेस्ट बोलने आया हूँ गुड लक थैंक्स सो दिस इज परमुटेशन ग्रुप्स ओके नाउ क्या है ग्रुप्स whatever we have learned what is that group so now the groups we learned are called abstract groups okay we don't see them in real life so permutations you can imagine na पांच ball hai you can just swap around and everything what college are I am in one NIT I am not disclosing the exact name so abstract groups are not I can't say it's not real but you can imagine this through math so this permutation and everything are described by an object that is called group so now I will not write the exact definition of group I'll just copy paste it from here I guess and I don't know wait so this is the definition of group okay so what's group group is basically first एक set लो I think I should explain it with a example, then it would be better, right? What's an example of group? I think n plus huh. So let's consider the whole numbers and plus. Okay, whole numbers and plus. Whole numbers means क्या है? Whole numbers means you'll have a set of 0, 1, 2, 2 and so on. That's the thing. And plus is an operation. So whenever we are defining groups, groups will have one set that is this one. This set is nothing but G and one operation. That's a plus in our case. So this is our operation. Operations are here called binary operations. Why? Because they are operating on two stuff. Like I can only let's say if there is an operator OP, yeah, so it will be A OP B we can operate on two stuff so it's called binary operator for this so first is G is closed under closed under that operator so let's say in our case whole numbers let's explore our first thing so let's say whole numbers if we add any two whole numbers for example okay do we get a whole number that's the whole point let A B belongs to G for all A B and G so A dot B belongs to G so can we get this let's say whole 1 plus whole 2. Will two whole numbers like this lead to another whole number? Yeah, it will. So that's why first criteria is correct. Now, let's move on to the second criteria. Second criteria says it's associative. Now, of course, like I can sit and explain, like I can go on with a bigger proof, but whole numbers are associative, right? Like if I write this, let's say a plus b plus c is equal to a plus b plus c. So in under whole numbers, it is very obvious. So I'm not explaining it in that much detail. You can prove this by just putting random values. Now identity element. Now what is identity element? I just told you a bit back. No, what is identity element? Identity element is nothing but when I will get some e. So in our case it will be a. Let's say a. That's our thing. A plus e will become e plus a is equal to a. That is the formal definition of identity element. In our case, 0 exists. So if I add 0 to any number, like pehle or later also, it will remain to a. So our identity is nothing but 0 in this case. Our third case is also true. Now let's see the fourth case. Says there's an inverse element, right? Inverse element means what? That we will, when we do any operations, let's say a plus some b will give me my e. That's the logic of um, my inverse element. So b is the inverse. Okay, that is the basic logic of inverse. Now, if you know our e in this case means identity was 0. So l- simple math, a plus b will be nothing but 0. That means what? B will be nothing but minus a. Now, of course, here you can see that minus a cannot exist. Like for take an example of a equal to 1. So minus a does not exist. So whole numbers and plus is not a group. But if we not didn't take whole numbers and 1, and let's say if we took um, real numbers and 1 plus real numbers and plus, that time this would be a group. So this would be a group. I took a very shit example. Sorry, it is not a group sadly. Just made one from scratch. So whole numbers and plus is not a group, and real number and plus is a group. So that's the basic logic about how groups work. These four, you just have to remember this four and nothing else. That's the thing. Okay. Now let's try to see some criterias of how groups work and what group is. So I think if I don't know if I have this in the book or something. Do I have it in the book or not? I have no idea. No, I'll just write it down. It is better because it's not that tough to write. So if this is the condition that first is that inverse is unique. How can we say that inverse is unique? Like, like if A ka inverse, let's say if A's inverse is A, let's say A to the power minus 1. Okay. So how can we say that this A inverse is the only inverse, right? We cannot say this. So how can we say this? So first thing we'll prove it by a simple method. Let's say we have B and C. We say B and C are the inverse of A. Okay. So what was my logic for inverse? That A B is equal to B A is equal to my E. I'm not writing any operator here. Just imagine that there is an operator. Okay. I'll just type it. I think that would be better. No, wait. So it will be A dot B is equal to B dot A equal to E. And also since C is also that, so A dot C is equal to C dot A equal to E. So this is my from my definition of definition of what do you call it? Inverse. Now, now. This is the thing. Now let's say if we also know that anything with its inverse is itself. So let's write this thing that B is equal to B dot E, which is okay. Now we know E is nothing but C dot A or A dot C. So we'll just do B dot A dot C. I hope this is clear. Now, if you see by associative law, we can do this B dot A dot C. It's associative, okay? So B dot A, here you can see B dot A is nothing but E. So we can write this as E dot C. Now E dot C is again C. So what did we find? B equal to C. That means if we have two inverses of A, right? They are nothing but same. So by this we can see that inverses are always unique. Okay. Let me see chat if something is there. Nice explanation. Thanks. I hope. Yeah, it will always remain on my channel. That is the only reason I did it on YouTube. In Twitch, you cannot do that. So I want that if I'm teaching something, let that be there for generations. So it won't get deleted. So yeah, this is the inverse is unique proof. Now can we say this? Ki, wait, I think I have a screenshot of this. I'll just do I have it? Do I? Yeah. Yeah, we have to prove these. Okay, this is the next proposition. Let me drink some water. So, yeah, so these are the propositions we are currently going to be working on. Is the audio visible? I have no idea. Yeah, the audio is clear. So, these are the propositions we are going to work with now. Okay, so A inverse is A. So, let's do the first one. So, it's nothing but we know that A dot A inverse, writing like this, A inverse is equal to E. This is the proof, no? This is the definition of inverse, na? A dot A inverse is nothing but E. That's the basis. Now, let's say if in the place of A, I replace A with A inverse. So can we say A inverse dot A inverse is also E? Because any number, see, since in group we know that inverse exists, no, in group. So if A exists in group, then A inverse also exists in group. And from the A inverse, the inverse property, we know that A inverse, anything into its inverse is E. Okay. And now we knew that okay, now can we write the above equation in these words that A1, A inverse is A. And can we reframe this as A inverse is A inverse. I know I'm saying too many inverses, but don't try to get confused. If you want me to repeat, I can repeat. No worries. So we literally proved in the earlier thing that A inverses have to be unique. So that means what? A is equal to A inverse inverse. Hence proved. The first is done. So we'll just give it a tick. I don't know. Let me do a different color. Yeah, first one is done. Now, second one is AB inverse equal to B inverse A inverse. Okay. Now let me try to do this. is that, let me write AB. We know that something into its inverse is always E. So let me do what? A dot B dot AB inverse is equal to E logically. That's according to our rule. Now let me try to find A dot B dot B inverse dot A inverse. Okay, I'm not saying this is E. We are trying to find the value out of this. Now can we rephrase this as A B dot B inverse A inverse. Now anything into its inverse is nothing but E. So we can write this as A dot E dot A inverse. Now we can remove the E because it's just the identity. So A dot A inverse. So finally it will become nothing but E. That means what? That means what? That means AB's inverse is this. AB's inverse is this part. So this, by that logically we can say this, no? Ki AB inverse is B inverse A inverse. So yeah, that is obvious. So let's try to prove the next one. AB equal to AC. Okay, let's say we have this thing. A dot B is equal to A dot C. That was our first thing, no? Let's try to multiply A inverse with both sides. A inverse dot A dot B is equal to A inverse dot A dot C. So nothing but A inverse A will become what? E. So E dot B is equal to E dot C. Then it will become B dot C. This one is very important. Remember this. This is called cancellation law. It's written here also. So this is what we are trying to do. These are the very three important rules you should know. I even give the proof so that, yeah. ग्रुप थ्योरी का यूज केस कहाँ पे आता है? ओके, ग्रुप थ्योरी का यूज केस you will get to know in your fourth or fifth semester when you will have automata. Basically what we look at computers is, right, like if I don't know if I can cover the whole thing today, but there is something called a finite state machine which I'll be covering later on, if not today, next week. So that one is basically we are trying to represent a machine or a computer through math. So अभी group theory का तो हम लोग begin किए है ना. So whenever we are on the ending stages of group theory, you will see that how we can represent computer as a if I'm not wrong, I don't have that much idea about the topic, but it's defined by 7 variables. So group theory will be very much important in that. Group theory is very crucial for mathematics plus computer science. You will not understand it now. Even I don't understand कितना use case होगा. मैथ में तो मेरे को पता है बहुत कुछ में आता है, but I can't tell about CS. CS में भी it has a huge amount of use case. So this was group, okay? And now if you see, group does not do commutativeness, no? So let's say A dot B is equal to B dot A नहीं होता है ना? So that's why what we can say, group is not commutative, but when it is commutative, we give it a special name called abelian groups. Okay, this is a short thing. Now we will define something. I don't know if I have the notes. If I have the notes, I'll just copy paste it. Yeah, I have the notes. This is what we're going to do now. It's called a subgroup. Okay, so let's say if there is a set, let's say there is G, simple thing. Let's say if I have a set S, let's for example, minus 1, 1 I minus I. Okay, let's define another set H, which is just 1 and minus 1. Okay, so S will be a group. This can be your exercise. You can prove it. S will be a group on multiplication. So S dot is a group. You can prove this as an exercise. Now see, we have a subset H of S, and now if we can show it is closed, obviously see, 1 into 1 is 1, it is there in S. 1 into minus 1 is there in S. Minus 1 into minus 1, 1 is there in set. So it's closed. Existence of inverse. Like, okay, does 1 have an inverse? That is minus 1. Does minus 1 have an inverse? 1. So inverses also exist. If these two conditions are satisfied, then we can say that H is a subgroup of S, or in this definition G. So how can we define a subgroup? A group is called a subgroup when it is a subset of the group and it abides by closure and existence of inverses. First proposition, okay, that all subgroups are groups themselves. So in, if you remember, the groups had four criteria, no? Closed under closed, associative, identity, and inverse. And out of this, this and this is covered by the subgroup. So we have to show identity and associativeness. I think so. Associative is very logical only. No, I'm not proof. Associative is one proof I'm avoiding because it's very counterintuitive. Like you can do it on your own anytime. You have to just calculate a lot. So I'm not doing this. This is obvious. I'm not doing this. So this one, let's say this is criteria 3. And number 4 is, I think, existence of an identity, right? So identity, see, A belongs to H and A inverse also belongs to H. And by the closure property, then A dot A inverse will also belong to H. That means what? E belongs to H. Means there is an identity in H. So identity element also proved. So if you have a subgroup is also a group. This is the proof. But it is not a definition of subgroup. Like you cannot say subgroup is a group. You write all four. No, subgroup is a definition. Simple subgroup definition is that it's a subset of a group and it follows closure and existence of inverses. Now we have to show that if there is, let's say, a H, let's say an H is a finite non-empty subset, then only closure is needed. What do I mean by this? Okay, let's say H is a finite non-empty subset. Okay, now let's say there is a H, the A belongs to H. Okay, so if it is closure, then A dot A also belongs to H. Then A dot A belongs to H. Means everything will be there. So what happens is that all powers of A will be in H. Since it is finite, since it's finite, all of these will not, like this is going on till infinity, right? So this cannot be unique and people will start repeating. So let's say if let's consider a repeating case where a to the power I is equal to a to the power j. This is a repeating case, for example. Okay. Okay. So by cancellation law, what can we write? A to the power j minus I. Remember the cancellation law? We literally did it a bit ago. Now can we write this as a dot a j minus I minus 1 equal to e? Okay. So if you remember that A dot B is E means B is the inverse of A. See, so A's inverse will be what? A to the power j minus I minus 1. That means what? Inverse exists. Inverse exists, no. And if inverse exists, that means it's a subgroup. And if it is a subgroup, then it is already a group. So that's why only closure is needed if it's a finite non-empty set. Subset, sorry. So that's my logic, okay? Let me see how much is left because I don't know. I am not reading it from like some notes or something. Just seeing it from two. I have two books in front of me and my own handwritten notes. So I have to just see. I think I'll do till cyclic groups today because yeah, even I have to study because I have exams. So I'll do a little bit by little bit every day. So I can't do discrete math for this long. Because discrete math is mind fucking subject, bro. Can't do this for long enough. Okay, let's talk about cyclic groups. Okay, we will not do the propositions. I'll just define cyclic group and leave it for today. Okay, so yeah. Okay, so let me take the earlier set we took. No, this set. Okay, this set. Okay, now let's take any element. Let's say a equal to I. Okay, what is a? I. What is a dot a? A square. I'll just write a square now. Minus 1. A 3 equal to minus I. And a 4 equal to 1. A to the power 5 is again I. So we can see a pattern. It's getting a cyclic pattern. It's like repeating after some time. You can, like if you can notice, it's repeating after some time. So this kind of graphs, so not graphs, sorry, this type of groups is called a cyclic group. This is not a definition of cyclic group. I'll give you the definition of cyclic group and explain it. It's better that way. Where is a definition of cyclic group, bro? I don't think this book has a written definition of cyclic book. Okay. So cyclic group definition is something like this. If each element can be generated, I'll write it. If each element can be generated by any one of the elements of the group, then then that group is cyclic. So, like, how can we talk about this? Let's say S here. We will redefine S. S will write something like G to the power I. Not I. Let's write K. It would be appropriate in this case. Where G is equal to I. I as in the imaginary number. I'll write imaginary. And K belongs to natural numbers. So we can generate all the elements. See, from I we can generate minus 1, minus I, and 1. So this G is called a generator element. So this is how we are working with the thing. So cyclic group is anything where we can take any one element and just take its power and generate the whole thing. Okay, that's the thing. So I will leave it till this, I guess. I will not, I'll just do one more proof that every cyclic group is abelian. How can we do this? How can we do it? Okay, so let's say there is a group, let's say we have two things, g to the power I and g to the power j, which belongs to g. Okay, very fine. So their multiplication will also belong to g. Okay, so how do we multiply this? This will become g to the power. I plus j. Now we know addition is commutative, no? So we can write this j to the power j plus I, and then we'll go to g to the power j dot g to the power I. So we can see that this is commutative, and since cyclic group is already a group, so we can say this that cyclic groups are always abelian. So that's the thing about cyclic groups. Okay. Now, now we have two more things. I'll just write this here. Wait, give me 1 second. Okay, these two are two things we need to prove, which I'm not proving today, but yeah, leave it here till today, and you can check it out. So this is the thing. So today we have covered a lot, bro, and I think end of this week we will finish the rest. We'll finish groups, and one more day we'll just do monoids and rings. So it will take, I think, 3 days, because it's impossible for me to teach for like 45 minutes I have taught, and that also, like, I have been in class since 4 to 9 to 5. So yeah, this is, we'll prove these two the next day,